Okay, all right, so we are in business. Welcome back, everybody. I hope everybody had a good break. Nice and relaxing, I hope. And now it's time to dive back in. So let me just remind you of our triple integrals to triple iterated integrals slicing process, right? And it's just like with double integrals, just more so, basically. So for the details, recall whatever variable you put on the outside. So we'll start off just as a starter example with dx on the outside. You slice perpendicular to that axis. Such a slice, of course, in this case, giving us this kind of whatever you would call that cross section right there. Okay. All right. First and last, of course, you find the bounds. Once you have those bounds determined, then we're going to fix a value of that variable. We're going to focus all of our attention now going forward for the rest, moving inside for the rest of this iterated integral, only on that value of x. Don't worry about stuff for different values of x. We'll get them for those values of x, right? But we need to know how the y and z bounds depend on x. So we focus on only one value of x at a time. Okay, so with x being fixed, focusing on this cross-section, we then move on to asking what's the range of values of y. Okay, so y will have a first slice and a last slice, thus giving us our y bounds. And then, with those determined, we fix a value of y. So now both x and y are fixed. We are now looking, therefore, only at this y slice of our x slice. And this being a three-dimensional integral, now we have a third slicing to do. And, of course, the remaining variable z. So we're going to look at the sort of bottom point there to get our lowest z-bound, and then we're going to look at the top point to get our upper z-bound, and now we're in business. Okay, how are we doing? Does everybody kind of remember this? We walked through this in gorier detail before break, but I just wanted to hit the highlights here. Now I'm going to point out a couple of things before we dive in and actually get our hands dirty and do some examples. Notice, as I've got commented down here, we still have this problem with how do I refer to these integrals, and first, second, third is awkward. What does first mean? As you're generating the integral, I would argue dx is first, right? But as you compute this iterated integral, dz is first. So the first, second, third is awkward. But I do think it remains reasonable to refer to dx as I have it here as being the outside integral. That's unambiguous. Right? And likewise inside for here. Conveniently, 3 being an odd number, the one that's second is second from either point of view, right? So you can actually call that one second, and that's fine. Otherwise, I like to call it middle. But anyway. Okay, all right. Further, notice that these bounds give you the range of values of the corresponding variable, right? But specifically, the range of values of that corresponding variable on the appropriate slice, or for the inside integral, as I have it circled here, for the appropriate slice of the appropriate slice. Right? So you have to keep in mind how these bounds are not on the domain as a whole, they're on the restrictions as I take slices in the process. Lastly, let me point out that for a given one of these integrals, let's take the dz integral then, in fact. Right? Notice that these z bounds are functions, and in particular, they are functions of the variables further to the outside than the integral in question. And this is a nice, pithy, convenient little rule. If you're looking at, let's say, for example, the dz, the inside integral here, it's the furthest to the inside. The bounds then are functions of the differentials, the variables for the differentials further to the outside, in this case, both of the other variables, x and y. How we doing? Is everybody with me? Okay. All right, so let's dive in and get our hands dirty. We'll do one. We've already kind of talked through all this stuff, so we're just going to move along to this example. I am going to zoom in a little better here. Okay, there we go. Right, so we've got here for our domain for our triple integral, we've got this tetrahedron. And it's a tetrahedron that's bounded by various surfaces. Note the equations of the surfaces are given in this case. Every question's different, obviously. So if I wanted to do a triple integral on this solid tetrahedron, and by the way, why would I ever want to do a triple integral on a solid tetrahedron? Well, oh gosh, there's a bazillion reasons. Maybe there's solid mass inside of here distributed in a weird way, and I want to compute the total mass. Or maybe there's, mosquitoes flying around in there. This is a little shelter that I've made in the woods, and I'm going to try to calculate how many mosquitoes there are in there pestering me, or whatever. Right? There's a bazillion examples of why we'd want to do an integral over a solid. We're not going to worry about that here. We want to focus here just on the process of converting triple integral to iterated integral. Okay. All right. So, here we go. Starting on the outside, you'll notice I have my dx differential on the outside, no particular reason. You can order these differentials in whatever order you like. Take your pick. For this example, it really doesn't matter. So just to get the ball rolling, I'm doing it this way. The subsequent examples, I'm going to switch around the orders of the differentials, again, just to show that we can, not that it really matters in some of these cases at least. Okay, so slicing perpendicular to the x-axis, I get slices that look like this, and the first and last on there I think are pretty easily pitched. That this is the first one. It's pretty obviously, see from the picture, it's in the YZ plane where x is 0, and so it's kind of hard to avoid. That's clearly 0. Right? Then we look at the last slice. That would be here. And arguably we have to do a little bit of work to figure out what that bound is. What is it, for example, that I know about this point? Notice it was not given. Right? This is not just listed, where the corners of the tetrahedron are. What I can do is identify that the bound I'm interested in is associated with that point. That point is on various surfaces. Those surfaces will have various equations. Remember, this is the sort of, connect the dots process that we talked about with double integrals. Just now it's surfaces instead of curves. So in particular, notice that point that I'm interested in. It's on that face of the tetrahedron. The picture tells me so. Thank you, picture. Got to have a picture to make these conclusions. That has this equation. Okay, let's see what else. It is on this face of the tetrahedron. Again, thank you, picture. That has this equation. What else? Well, it is on this face of the tetrahedron. Again, the picture is necessary to see which of these given equations from the statement of the question is actually relevant to the actual point that represents the actual last x slice. Right? You've got to have a good picture. You're going to hear me say that about 1 million more times today. Okay, so that face has that equation. So if you want to understand, as I do, the x-coordinate, right? The x-coordinate of this point representing the last x slice, I need to solve for x in this trio of equations. Everybody on board? Everybody see where they come from? And again, one thing you want to resist in this circumstance is resist the temptation to kind of say, well, yeah, but I can just kind of solve the heck out of that whole tetrahedron, right? And I can just see where that point is, right? We're not interested in the answer here. We're interested in the process. There will be examples coming where you will not just be able to, I can just, write down everything. Everything's obvious, right? I'm interested in focusing on the process. The bound comes from this point. That point is on these three surfaces that have these three equations. I'm looking for an x bound, so I have to solve for x in this system. Everybody happy? Okay. And of course, that easily solved, and that gives me my upper bound. Okie dokie. So now let's move along. We found our x bounds. We're going to fix now a value of x. So we're going to look entirely on this x slice. We move on now to y bounds. What do y slices look like? If I slice perpendicular to the y-axis, oh gosh, art. Something kind of like that, right? We've got this x slice like this. We're going to cut it with a y slice like that. And again, those slices of slices look kind of like this, right there. Everybody on board? Right, first and last. First one's over here, clearly in the xz plane where y is clearly 0, and so it's kind of a freebie that the y bound is, lower bound is 0. Again, sometimes you get lucky, don't count on it. Won't always happen, but when you do, how handy. Okay, the upper bound. Now, again, a little bit more worrisome, right? A little bit less sort of immediately obvious. The upper bound, I got it. Okay, comes from this point. Now, again, I have to rely on my picture to figure out what is it that I actually know about that point. And, well, the first one is staring right at me as it happens. That point is on my existing x slice. Now, this is my own little sloppy shorthand for this, just to represent that x is known. I am on a given x slice. I just write x equals x, and I know it doesn't mean anything, right? That's tautologous. But I find that satisfying somehow, right? You don't have to do it if you don't want to. But what else do I know about this point? And, well, I know that it is on that face. See it right in the picture. Gotta love the picture. That face has that equation. And furthermore, it is on this face. Thank you, picture. That face has that equation. So again, reminder, what am I doing? Why am I here? I'm trying to find an upper bound for y at this point, so I need to solve for y in this little trio of equations. And again, the actual legwork on that is pretty easy. And we get that, and that is my upper bound for y. Everybody happy? Okay. All right, moving along. So let's see here now with y fixed and x fixed. So x still fixed. Well, let's see here. X still fixed, y still fixed. Looking at this y slice of our x slice. On that slice, I now want to know the range of values of z. Z starts where z is obviously 0. Gotta love it. Get lucky sometimes. Z ends, though, at this point. What do I know about that point? Again, repeating the process. I obviously already know x and y. Now, again, I have to consult the picture, and there is something about this picture that allows me to see the third piece of information that I need, and I can see from the picture that that point determining my upper z bound is on that face, which has this equation, and I am looking for a z bound, and so in here I need to solve for z, and that gives me my upper bound for z. Yeah? Everybody's good? Yeah.
When solving for like the most inside variable, is it always going to be the case that x equals x and y equals
you will, when you're looking for your inside bounds, it is always the case that the outside variables have been set, and that yes, you can treat them as known. Yeah, absolutely. Was that what you were asking?
Yes.
Yeah. Okay. Yeah. Cool. Okay. Alrighty. So that's the deal. Now we have a bunch more examples. Part of the reason I'm going to show you a bunch more examples is because this is hard. It's three-dimensionally challenging. It's artistically challenging. There is a delicate process that has to be followed very carefully, right? So this is worth spending a little bit of time on. But it's this process, pretty much, in all of the examples to follow. A couple of quick observations. Yeah, you've got 6 different ways that you can order these differentials. So, try to make good decisions on that. Now, how does one make good decisions? I'm going to give you the same 2 sort of bits of advice. Try not to slice through corners. Morally equivalent reasons to why we came to that conclusion for double integrals. And also, if one of the variables is more naturally a function of the others, right? I mean, think about what you want to solve for and what you don't want to have to solve for, and whichever one you'd like to solve for, put it on the inside, right? So that will be the one that you have to solve for, so you get your way. The third little bit of advice is something that's going to take some sort of dirt under the fingernails to really see what we mean by all of this. So I'm going to momentarily skip this. I'm going to dive into the next example, and as we sort of start going through this next example, I'm going to come back and explain what I mean by these observations here. But it's a really good trick. Okay, so starting with here's our region R, and it's this thing here, which is really hard to draw. So the first pitch I'm going to give you is, and you've heard me say this before, this course is unavoidably intrinsically geometric. And to help you understand these geometric ideas and to help you communicate your geometric understanding, right, both of which, again, are intrinsic to what this course is about, it's really helpful to be able to draw a decent picture. Now, drawing three-dimensionally is hard. Nobody is born knowing how to do it. Some people, I don't know, some people maybe have a knack or something, right? But there are tricks to it. There are things to know, and best to have these pointed out to you for free as opposed to having to slowly, painfully figure them out for yourself. So I have a video on my YouTube channel. I hope you'll find it useful. As with many of my videos, it's in the miscellaneous topics playlist. Actually, there's 2 of them. They're called Drawing 1 and Drawing 2. And if you feel like being able to make a drawing like this is beyond your capabilities, then I strongly advise that you watch those videos. And in particular, this exact drawing is one of the several, hands dirty actual drawings that I walk through, and so every little aspect of every pen stroke that makes this drawing, I discuss and motivate in detail in those recordings, and a few other drawings as well. So I think it'll be really helpful. I hope you'll find it useful. All right, so here's our shape, and now how are we going to slice this up? I very quickly notice that in the statement of the question, there's a pretty good persuasion right away that I'd really prefer to not have to solve for x or y if at all possible. So that my favorite variable to solve for here is going to be z, right? Because it's already solved for. It doesn't require any square roots. And so based on that alone, I'm thinking I want to put dz on the inside, and therefore dx and dy on the outside. All right. In fact, why don't I do okay, yeah, I think that'll be good enough. Okay, everybody on board? Okay, now you can, I suppose, start slicing it up, just like we did with the last example. But then it gets really hard to draw. So you'll notice I have dy on the outside here. Again, no particular reason between the dx and the dy. I could have done that either way. In this case, that particular choice doesn't matter much. Slicing perpendicular to the y-axis, I get slices that look kind of like that, and it's hard to draw, right? So, it'd be nice if we had a way to kind of avoid all of this 3D drawing geometric challenge, or at least minimize it as much as possible. So here's where this projection business comes in, I think, very nicely. Rather than go through and looking at this slice and then thinking about slices of the slice and relying on so much on the picture, I'm going to claim here that there is what I call a good, we'll elaborate on that in a second, a good projection down into the XY plane. And in particular, if you take this solid and imagine what its shadow looks like down here in the XY plane, I claim that that's a good projection. Now let me detail what I mean by that being good. Comes up to here. The shadow is a reasonable shape. There's nothing horrifying or super weird about the shape of this shadow. Now, in this case, again, I can just kind of look at the picture and see that shadow is a quarter disc, and it's not my favorite shape. I think my favorite shape is a rectangle, right? But beggars can't be choosers, and in this case, this is just as good as any of the other shapes I'm going to be might have to be dealing with. It's an intrinsically round thing. Okay, so a desirable shadow. And now I'm going to say the top and bottom surfaces are consistent and desirable. Now I'm going to have to walk through what I mean by the top and bottom surfaces. Okay, so what we're eventually going to be doing is, having chosen to do a projection to the XY plane, we're going to put X and Y on the outside. In fact, I think I have that written up here. Yeah. Those two variables on the outside. Putting our X and Y on the outside, which means that we're eventually going to have DZ on the inside. That means when it comes time to figuring out these inside bounds, those inside bounds are going to be in the Z direction. And it's just a consequence of the shadow that I've chosen to look at, how I'm setting up this projection. And notice that for those bounds, right, as I look for the range of values of Z, notice two really nice things. One is that bottom point that gives me my lower bound for Z. Notice it's always on the same surface. It's always on that paraboloid. Consistently. That applies for this whole shadow. For every point in this shadow, the starting value of Z, always on that paraboloid. And back up to the rule here, consistent, because it's always the same surface, and desirable in the sense that, well, how would I solve for Z? How would I figure out what that Z bound is? Well, it's pretty desirable. I mean, I can see it right there in the equation. It's easy to solve for Z. And again, it's not a constant value of Z. I suppose that's the most desirable. But again, if you had to pick something, a polynomial is not that bad, right? Better than an inverse trig function, right? I think we'd all agree with that. Okay, so consistent and desirable lower surface. Okay, and then now let's talk about the upper surface. The upper surface, let's see here, and just for artistic reasons, I'm going to do that. The upper point giving me my upper value of Z, again, consistently always on that one simple surface right there, which again has a desirable equation. In this case, about as desirable as you could get. It's a constant. Right? So this is what we mean. This is what I mean when I say that we have a good projection. The shadow looks fine. The lower bound surface is always the same. The upper bound surface is always the same. When you have that set up, something really nice happens. And here's the really nice thing. When you set things up like this, and when you are trying to figure out, for example, what's the range of values for your outside two variables, for your projection variables, x and y in this case, because I'm projecting into the xy plane. The awesome thing is that the range of values over the solid is exactly the same as the range of values over the shadow. It's beautiful. And that means that I don't even really have to do any slicing on my solid. The solid was weird and hard to draw, and it's even hard to draw the slices. I don't have to, because the range of values of x and y on the shadow will give me the exact same answers. And you can just see it from the picture, right? Any slice I might take, for example, here is a slice of my solid. Well, its shadow is a slice of the shadow of the solid. So I don't need to look at this. I can just look at this. It's a big win, artistically, if nothing else. So notice with this in mind, and I'm going to now erase I don't need to even look at my solid. Look, I've got a real simple two-dimensional little picture down here to draw. Right? This edge here is just a circle. Really easy equation, really easy to solve for what I need, and it's basically a double integral analysis, and really easy, therefore, to find these bounds. Everybody on board? So nice trick. I'm a big fan. Underappreciated, I think, my experience. All right, with that observed, I mean, we're mostly there. We've kind of already agreed that the lower bound for z is going to come from this. We've already observed point on this consistent and desirable lower bound surface, and so I just solve for z, as I've already agreed I'd like to do. And for the upper bound, always again on that surface, again very desirable, solve for z, and easy upper bound. Everybody okay? Nice little trick. I'm a big fan. All right. Let's get rid of the mess here. Let's see another example. So here we have the unit ball. Now, again, you can slice it, and you can slice the slice, and it's harder to draw than you would think. Give it a try if you don't believe me. It's tricky to make it look kind of right, kind of, the slices actually look like they're inside of the thing, and to have it not sort of just be disproportionate and just weird looking. Tricky draw, which you can do, and you can go through the game and et cetera, and you can justify that this is what your final answer will be, and fine. And by the way, notice I'm doing the differentials in yet a different order here, arbitrarily. Again, in this case, it really doesn't matter. Everything's kind of round. All the variables are kind of playing the same roles. So let's use the shadow trick, right? The projection trick, to see if that can save us some trouble. Now, just to be consistent with what I've already got on the page, let's think about the projection, the shadow of this solid in the XZ plane. And whether it's easy to draw or not kind of isn't really the point, but it's certainly easy to understand that the shadow of a sphere in a plane is going to be a disk. Right? This is a ball of radius 1, so that shadow is going to be a disk of radius 1, which is easy to draw, easy to slice, double integral arguments, and look at this, we're 2/3 of the way done with our triple integral, and we've hardly done anything. Everybody with me? It's a really nice trick. Okay, and so now again I've got to think about, okay, what's the upper bound surface and what's the lower bound surface, and I argue that as y, for a given x, for a given z, as y varies, and I'm just going to come over here sort of out of the way, the starting value of y is going to come from a point that's on this back hemisphere. The ending value of y is going to come from a point over here that's on this sort of front, if you will, this front hemisphere. And you do have to then solve. Let's see, again, we're looking for y bounds. We've got y on the inside, so we're going to solve for y in the equation of, I'm going to have to write down the equations of these two hemispheres, and do be careful, please. It's tempting to think of, again, of square root as just magically undoing whatever squaring process is involved. Not so. You do have to realize that for the lower bounds for y, per the picture, I need to pick the negative square root when I'm solving for y. For the upper bounds, I need to pick the positive square root. Again, the picture shows. But that being said, easy to solve for x and y in those equations. The upper bound is that. The lower bound is that. And again, now we're in business. Everybody happy? All right. Okay, here's a really tricky one. A couple of things I like about this. For one, this is a nice example of a, what I'm going to call a drawing trick that I think is good to experience, good to kind of, a good lesson to learn in the classroom instead of in the real world. So it's a nice example of that. And it's another great example of a projection. The other thing I like about this example, it's a great refutation of something that those who have taken a high school multivariable calculus course are likely to have seen, which is, again, this sort of assertion that you can kind of just see what the bounds are and the integrals. You kind of look at you can pick out in some of the algebra that's given, it's pretty clear what goes where. Absolutely not. Absolutely not, and this is going to be a wonderful example of that. Okay, so here we go. We're going to start off with these five surfaces. Pretty scary. Think about it. Trying to figure out how 5 planes, even planes, right? What if they weren't planes? What if they were weirder surfaces? How do they sort of intersect? And what in particular is bounded by, right, those 5 surfaces? Thankfully, planes in this case. So very intimidating. Here's the trick for drawing. I think this is very helpful. You will notice sometimes that several of the equations in your list have a variable missing. It won't always happen, right? Again, but sometimes you get lucky and you notice these 3 equations here, there's no y's in those equations, and I'm going to refer you back to an observation we made back in chapter 1. If there's no y's in the equation, then those planes are then parallel to the y-axis. And so that makes them easy to draw. I can, in fact, just kind of draw them. Here's z equals 0. Here's z equals x. Here's x plus z equals 2. You'll notice I'm just drawing them in the xz plane. They're just lines in the xz plane. That's easy. And then, but wait a minute, these are actually planes in space, and furthermore, I know they're parallel to the y-axis. So I just kind of do like this. Just kind of stretch them out like that. And so I've got 3 of my 5 planes drawn now, and I already kind of geometrically see a lot of what's going on here. I've got a prism type shape here. And again, the key observation, the thing that made this all kind of hold water, is that I identified several equations that I'm given that all had this conspicuous feature of missing y's. And it won't always be y. Maybe it'll be x, maybe it'll be z, whatever. Okay. All right, so once we've got that done, it's kind of filling in the blanks at this point. Y equals 0 is just going to kind of slice through the prism to make that left face there. Yeah. And then let's see, now the hard one to draw, and this one's a little annoying, x plus y plus z. Okay, so that one, it's going to be, something like that maybe. And now it is tricky and challenging to think through, okay, how does this angled plane cut through this prism? And one thing you could do, by the way, is actually solve for these intersection points. And knowing exactly what the x, y, and z coordinates are for those 3 intersection points might make it a little bit easier to kind of draw and see how this thing ends up looking. But anyway, so that intersects then with this face like that. And thus our picture. So, everybody happy with that? Yeah. Okay. All right, so with this observed, again, you can start thinking about different ways to slice, and I think it's a healthy exercise to go through and start slicing in different directions and then start slicing your slices, etc., until you decide that you want to abandon one of these possible 6 orders. So, for example, notice if I start slicing perpendicular, perpendicular to the x-axis, right, something like that, notice I'm going to hit a corner. So I don't like that. Right? Likewise, let's see here, if I were to slice, perpendicular to the y-axis, like this, notice I will eventually hit this corner, after which my y slices change in appearance and they start to look kind of like that. At which point I will hit this corner. Oh my gosh. Okay, so slicing in the dy direct, in the y direction first would be catastrophic. I'd be hitting 2 corners. Right? We'd have to break it up into 3 intervals. We really don't want that. Okay. So again, think through all these different possibilities for yourselves. I claim, as it turns out, that this is the only way to do it that won't hit corners. And again, it's good little mathematical, geometric weightlifting to think that through, draw the pictures, hold yourself to a standard on the pictures as you draw them. It'll be good practice to get you, doing a good job with your diagrams and thinking through the geometry of it all. It's challenging, but a healthy exercise. And this is the only one that avoids corners. Okay, so, but, again, let's try to avoid a lot of work here and think in terms of what's a good projection. Now, let me show you a bad answer. Here's a bad attempt at a projection. Let's think about the shadow down here in the XY plane. That is a really bad choice for a projection. Because on the one hand, while I can say, oh, look, if that's my projection direction, then check it out. My lower bound is always that same surface. That seems pretty good, right? That's nice. But what is my upper bound surface? My upper bound surface is, well, it's that for a while, for sort of these points in the projection, but it's this for those points in the projection. Our upper bound surface is not consistent. My upper bound will sometimes come from this green back face, and it will sometimes come from this purple front face. And so again, this is not a good choice for a direction of a projection. Everybody on board? So what is a good choice? Well, you can probably guess from our slicing claim here, but I claim that the XZ plane is the good choice. And here's the shadow in the XZ plane. The lower bound surface is that same surface. The upper bound surface is consistently this face here. I will always, if I project into the XZ plane that I have in yellow here, my lower bound will always come from that orange face. My upper bound will always come from the purple face. Cool. No problem. And so details to be filled in. So I want y'all to think this through. But if you project, color. If you project into here, that triangle, you slice up in the X and Z directions and get these bounds. Make sure you can fill in those blanks. Right. Your lower bound is going to come from solving for Y on this face, which again, sometimes it's easy. Right. Your upper bound will come from solving for Y on this face. A little bit of algebra to be done there, and you get that. Everybody happy? It's a hard question. Okay, another hard one, and I'm going to be quick with this one because a lot of the same ideas we've already talked about, but what I like about this one is it's really hard to draw geometrically, right? Notice I didn't even draw an example of the slices myself, right? Because I think I can persuade you that we don't want to have to do that better without a poor attempt and fail on my part, right, in the picture. So it's very, very difficult to draw the slices. Certain things jump out at you, I hope. And let's see here. Let me to fit as much as possible on the screen. Notice Y is the one I'd like to solve for. And so motivated by that, I'm going to put dy on the inside. Right? Also, notice I claim we have a good projection into the XZ plane. Think about what that shadow looks like there. Right? That shadow in the XZ plane. And everything's nice if I put those on the outside because my lower bound consistently comes from that surface and my upper bound consistently comes from that surface. And so no problem. And all sorts of horrible things happen if you slice in a different order. Right? If you project to the YZ plane, for example. You don't want to do that, right? It'll get super ugly super fast. Okay. So if you project in that direction, notice that our projection is easy. That's just a disk. A couple of details to think about what the radius of that disk is, et cetera, but that is easy to slice up in a double integral sense. And then the orange surface, and of course now you do have to make sure that you can keep it straight which of those equations is the orange surface. That's this one here, and you solve for Y, and you get that already solved for. Again, part of the reason we did it that way. And then this surface is that one. And again, solve for Y. Again, already done. Again, that's why we did it that way. And you get that. Everybody happy? Okay. Moving along. So that's triple integrals. So section 5.5. Now, this is another one of these weirdly big sections. This one really ought to be, I think, 3 separate sections. But our textbook makes it one monster section. It's going to take us a while to get through this monster section, but you'll notice on the content syllabus I've broken it up into 3 parts myself, and that'll be helpful to us. Change of variables is the topic. Y'all may recall, I assume that y'all recall the substitution rule. From single variable calculus. It's one of our, people call it integration techniques. And I've written it here as a statement about integrals Very often it's stated as a statement about antiderivatives. It's fine. This is what it looks like when you write it down as a statement about integrals. So I hope this looks familiar, right? Okay. I know y'all understand this. I am not going to reteach single variable calculus, right? But what I am going to do is I'm going to take a particular point of view on this. Y'all have noticed, I'm sure I do this sometimes. I like to take a particular angle on something you already know, because that particular angle is what will allow me to most conveniently, bump it up to a multivariable version. So here's the particular angle that I now want to take on this. I don't want to think of g here, the function that we're using to relate t and x, which here it is. There's g, and I'm going to write explicitly, g of t is x. I don't want to think of this just as an algebraic thing. Very often in single variable calculus classes, it's all algebraic, and you write down certain bits of algebra and you plug this into there, and stuff like that. I want to think of this actually as being an actual function that takes me from a domain, namely the t-axis, to a target, namely the x-axis. And in particular, that allows me to take this interval from A to B on the t-axis and think about what its actual image is. Its actual image over here, of course, is g of A to g of B. Okay. Let's think about this more sort of geometrically and less algebraically. So there's a couple things going on with this geometric point of view. First, let me talk about what I call the stretching factor. If you have some little piece of the domain over here, naturally we'll call that dt. dt represents the size of this little piece of the domain. Now I'm going to twist that just a little bit. Yes, it's a size, but let's think of it equivalently as representing a change. As I go from this point to this point, as I go from the left side of this little subinterval to the right side, t changes by some amount, dt. I'm going to call that not a size, I'm going to think of it as a change. Likewise, as I do that, notice in the output, right, x will change by some amount, dx. And so we have an input change and we have an output change, and hopefully, again, knee-jerk reaction, semantical clue, what's the relationship between input changes and output changes? And we know that the derivative, right, g prime, is the thing that I multiply by input change to get output change. And so I can write this relationship down, not thought of algebraically, moving differentials around, but thought of geometrically as by what factor has this thing, this little piece of the domain, been stretched out to make a, as I have it drawn here anyway, larger piece of the target. Is that cool? Okay. All right. So this concept of a stretching factor, and again, it seems a little forced. You don't have to think of it this way, obviously, but again, taking a very specific point of view because it will help us generalize to a multivariable setting. So that's what I mean by a stretching factor, is how much bigger are pieces of output compared to pieces of input. And you can see, of course, what I'm doing with that. This great big thing, dx, I'm just going to write down the formula for it right there. And this brings me to the second, well, I guess I listed it first, but the other of the two big points, perspectives that I want to push here is that there is a pulling back sort of aspect of what I've written down here. So notice the function g goes this way. Inputs are over here, outputs are over there. But as a result of the function going that way, I argue that expressions go the other way. I just rewrote dx in terms of t. And likewise, if I just literally plug in my function, right? x equals g of t. Okay, well then x turns into g of t. Basically, and this is not that deep of an observation. It's a little unexpected and weird and hard to digest, I suppose, but the act of plugging in turns expressions backwards, right? Outputs turn back into inputs in some sense. So this is the idea of a pullback. So what we're going to do next time, I see we're out of time now, but what we're going to do next time is we're going to talk about how to use these two ideas and make sense out of, roughly speaking, a substitution rule in a multivariable context. Y'all have a good rest of your Wednesday. See you later. See you on Friday. Whoops. Yeah, sure thing. See ya.